Hello, everyone. Thank you for joining us today. My name is Stephen Hanley. I'm a mechanical engineer at Mide Technology. We get a lot of questions from customers of our slam stick vibration and shock data logger line of various different aspects on shock and vibration testing. So I'm excited today to share what we've learned over the last couple years and from our own experiences with you all today. And hopefully you'll leave in the next hour knowing a lot more about shock and vibration testing, but more importantly, know where to go to find more information. So let's get started. Today we have a lot to cover in a fairly short period of time, so we'll be moving through things fairly quickly. We'll start with just why you need to set up the testing, and there's some questions you need to answer before you can go about your hardware selection. And then we'll get into that, how to select the right sensor and right data acquisition system for your needs, how to set up that equipment once you've selected appropriate equipment. And then we'll get into the fun stuff, which will be the analysis, and we'll get into some spectrum analysis, response spectrum plots, and I'll also show you some software packages that are available. To conclude this, I know this is there's a lot of stuff out there, so I'll give you some links on some resources, and we'll have a brief Q&A. So one of the most important things before you can set up any shock or vibration testing is you need to answer some questions, some basic questions, and we'll go through those now here. One of the best definitions I've found for shock and vibration measurement is from one of the books that I included at the end of the slideshow here. But the definition is shock and vibration measurement is the art and the science of measuring and understanding a structure's response to a dynamic event. I really like that definition because it implies that there's a lot that goes into it, and it's not really cut and dry. It's not just a scientific process here. There is definitely some artistic things you'll need to do to effectively set up your equipment and also to analyze the data. Everything you see and touch can vibrate. So the technical definition is all bodies possessing mass and elasticity are capable of vibration. And again, that basically just means everything you see and touch can vibrate. As we have this world that's becoming more and more automated with more and more powerful machinery, vibration is becoming an ever increasing thing to think about as design engineers out there. Those two plots on your right, one of which is just a simple spring mass damper system that we'll talk about later on. And there's also a nice little video here, if I can get that to play. Let's see here. That just shows you that mass damper, or that mass moving up and down. This was downloaded off of one of the resources I included at the end. So some key terms we'll talk about throughout the slideshow is frequency, which is just the rate at which something is oscillating. The amplitude is that level of oscillation, and then stiffness, which would be your spring stiffness, it defines your elasticity, and then damping, which is often used. They use the Q quality factor, which is equal to 1/2 of the damping ratio. So now we've got those things out of the way, let's get into some good stuff. So these are the questions I keep talking about that you need to have answered before you can go about doing your shock and vibration testing. The first one is the frequency range that you need to measure. I've seen far too many times engineers select a sensor that is just not appropriate at all for the frequency range, or even their DAQ system might be the wrong one to use for a given frequency range, and you get erroneous results. The amplitude range is somewhat self-explanatory on the surface, where you need to have a sensor that has the appropriate amplitude range for what you need. But you have to dive in a little deeper. If you have trying to measure really small vibrations or shock events, you'll need to make sure your sensor has very high sensitivity, very low noise, and the same would go with wiring would have to be very noise shielded. Your DAQ system would have to have very good resolution. On the other end, though, if you have trying to measure shock events, you need to make sure that your sensors and hardware and wires can survive those events. Who needs the data and why? A lot of you guys will be doing some testing for the U.S. Navy or some other military group. There's a lot of test standards out there, like Mil Standard 810, general environmental things, and then 901Ds for shock you'll see a lot. But these test standards can be something that you should look at before you set up the test, because actually a lot of the standards will go through sensor selection and various things and best practices to use. So it's good to understand what you're doing it for. And then if you have a customer that maybe isn't as intense as the U.S. Navy or yourself, you can maybe go about getting cheaper equipment or something that give you kind of quick and dirty results. So it's good to know who you need to do the testing for. Where the test environment is definitely pretty critical for the type of sensors you're going to select. It also defines where your data acquisition system and other hardware is going to live. If you're out in the field, you're going to have to make sure you have pretty rugged equipment. Whereas if you're in the lab, you're not going to be as worried about wires, and your DAQ system will probably be a computer that's just right next to whatever test setup you have. So it's critical to understand that. When the test date is, I bring that up because a lot of this equipment has fairly long lead times. So you'll need to pay attention to that when you have a test. And I've worked with customers who a lot in this field that's they need something because a test went poorly, or they were doing something and their equipment broke, and now they need emergently to figure out why. And if that's the case, you're going to have to forego certain sensor types because it just takes too long to get them. And then when the vibration analysis need to be completed by, that's something else to bring up, because if you just need, again, some quick information, you're going to maybe be able to go the route of a cheaper software, or if you have a couple months available to you when you have a development program to really dive into the software, it might be worthwhile to get a more intense system. So it's really good to spend a decent amount of time think about these questions before you proceed with actually setting up your test. Now that we've gotten that out of the way, we can talk about the hardware setup and some specifics. So the main sensor for shock and vibration testing would be an accelerometer. The next slide, I'll talk about some alternatives, but accelerometers are definitely the way to go for most applications. There's three main types, being piezoelectric, capacitive MEMS, and then piezoresistive. The piezoelectric accelerometers are higher end comparative to the capacitive MEMS ones. You'll see them in most applications where you have those little stud-mounted accelerometers wired to a DAQ system. They're great all-purpose accelerometers. They're good for shock testing. They're good for vibration. The one thing that is key to note is that they're AC coupled, which means they can't measure static accelerations like gravity. And it's something that gets lost on certain customers that I've talked to repeatedly. As they see accelerometer, they expect to see that 1G offset when it's on a desk, for instance, to show the gravity vector. But piezoelectric one does not have the ability to measure the gravity vector. For some applications, that's actually good. It's a form of high pass filtering. But some applications like human motion, for instance, and other things, you'll want that DC coupling so you can measure gravity. Capacitive MEMS accelerometers are DC coupled. They're pretty cheap, easy to get. They're surface mount accelerometers that are in your phone, on the order of a couple dollars. Piezoelectric and piezoresistive are typically around $1,000 or so. And capacitive MEMS are great. They're cheap and easy though, and because of that, you kind of get not the highest quality data for certain applications, but for human type motion, lower frequency and amplitude, that's a great sensor to go for. Piezoresistive are the premier for shock testing. So the DC coupled, which is important when you're doing shock testing, because a lot of times you'll want to integrate the data to get velocity or displacement. It's hard to do that with piezoelectric accelerometer. So there's a nice table there on the right that we have on our blog. And actually on our blog, I wrote an article about more in depth on sensor selection here. So, but use this table here as a nice reference for different applications in which sensor type is best for you. But let's talk about some alternatives to accelerometers. So for alternatives, you can look at vibration meters for one, which you'll see a lot in industrial applications when they're trying to do equipment maintenance and monitoring. They used to in the past have an accelerometer wired to this vibration meter, but now you can get some that actually have the accelerometer embedded in it. These are good for the go no go testing of your machinery to get an idea of the RMS level of your vibration. It will sample relatively quickly, so it'll give you a resonant frequency and amplitude, but it won't give you the ability to have a lot of time domain data, so to do much analysis on it. It's really only good for that go no go type of testing. Vibration data loggers will have the sensor embedded with the data acquisition equipment and power as well. So you can consider your phone really actually a type of data logger, a vibration data logger, and there's some apps out there that use the accelerometer in your phone. And there's some other cheaper data loggers out there to look at that are a couple $100. Obviously, our product here, our Slam Stick, I'll plug a little bit, but I do think it is a higher end data logger that bridges a gap from the cheaper alternatives like in your phone or the couple $100 ones that you'll see, but it bridges it to the wired higher end piezoelectric accelerometers. And our Slam Stick actually has the ability to have the capacitive MEMS accelerometer in addition to either the piezoresistive or piezoelectric. So you kind of get the best of both worlds. Now, if you don't want to use accelerometers at all, you can actually use non-contacting displacement sensors. There's a couple types. There's laser displacement sensors. You can also use Hall effect sensors. And these are great for measuring rotation, or if you're trying to measure the vibration of a piece of equipment or whatever that has a small amount of mass, and your accelerometer would be too much mass and it would actually, alter the vibration of that thing. So you need to use some non-contacting sensor. The trouble with these type of sensors is they measure relative displacement, not absolute. So, it's measuring the relative displacement between where your non-contact displacement laser is versus what it's measuring. So sometimes it might miss, if both things are moving in unison, it will look like your test equipment is stationary when in actuality it's just moving in unison with your sensor. The other thing with these is they're relatively fragile, so they're not used out in the field very often, or think of other applications like that. The type of sensor that people forget about for vibration testing sometimes are microphones. Sound is vibration in the form of pressure waves. So you can use microphones in the cheap way, where you just use sound levels to determine relative vibration amounts. But you can even dive in a little deeper and get frequency content from sound. And there are high-end microphones out there specifically for acoustics and vibration testing. So those are some alternatives to accelerometers if you want to go that route. Before we get into some specifics on your data acquisition system or DAQ, you have to think about the mating between the two. Is the output a digital or analog output from your accelerometer? If it's digital, you just have to pay attention to the interface it's using. Is it I2C? Is it serial? What is it? If it's analog, you'll have to pay attention to the voltage range output and make sure that your DAQ system can handle that. The other thing is some accelerometers will output in millivolts. You'll need to have an amplifier in there to amplify the output before you convert it to digital. The other thing is some DAQs will actually provide power to your sensor, which will really simplify the system and reduce the number of wires you need. So that's something to consider too. So one of the main things that a data acquisition system, one of their specs will be is the max sample rate. It's good practice to sample at least 10 times greater than your max frequency. That might sound like a lot, but undersampling can miss important data. On the right here, I have some vibration data recorded with our Slam Stick when it was on the outside of an aircraft. That blue line is the output of the accelerometer with the 2500 hertz sample rate. The dashed red line is if we had an accelerometer only sampling at 500 hertz. You'd see that it would be grossly misrepresenting the data and missing a lot of information in there. So it's really important to sample 10 times greater than the max frequency of interest for you. Digital sensors will have a fixed output rate, so sometimes that can be a little difficult for you. It will typically be an order of 2, and there's not much you can do, so it really won't drive DAQ selection that much. Some general guidelines are that for shock testing, you should be sampling at over 10 kilohertz. You'll miss the peak otherwise. For typical vibration environment, you'll need a couple thousand hertz at least. And then for general human motion, 1 kilohertz would be fine. You can maybe get a little lower too if you know that you don't care about higher frequency vibration or shock events. But the key takeaway is that you need to sample quite a bit faster than the frequency range of interest. The other key parameter you'll see of DAQ systems will be its resolution. This is normally specified in bits, and you use that to calculate your resolution and acceleration unit. So that's done with you raising the number of bits by a power of 2. So let's say, for example, you have 16-bit resolution. 2 raised to the 16th is 65,536. You have that many number of bits. On the right, I just have a plot that shows the blue line being 5-bit resolution and the red being 3-bit resolution. And that just shows you how you're going to have missing a lot of data if it has to round off to the nearest bit and you have relatively low resolution. Good DAQ systems typically have 16-bit or more. You'll see 24-bit in some, and generally you should be wary of those that have 12-bit resolution or less. For example, if you had a 100G accelerometer, measurement range of 200 Gs, plus or minus 100, 16-bit resolution would give you the smallest increment of measurable acceleration being 0.003 Gs. But if you had 12-bit resolution, you can only measure down to 0.05 Gs. So again, that's why you need to think back to what you're doing the testing for and the measurement range of your device. If you don't really care about the lower amplitude stuff, you might not need as good resolution, but it all depends on the application. Now, most DAQ systems will have a low-pass filter built in, and you need filtering to prevent aliasing. Once a signal has been converted to digital, there's no way to software filter out an alias signal. So what is aliasing? That plot on the right shows in the blue line a 60 hertz sine wave. If you were sampling that 60 hertz sine wave at 100 hertz and you didn't have any filtering, the red dotted line would show you what would look much like a 40 hertz signal, when in fact it isn't. It's a 60 hertz one. You really need to filter that out. So be wary of any systems that don't have low pass filters. You'll need to make sure you have that to prevent aliasing. But the question remains, what type of filter? So let's talk about that. So an ideal filter would uniformly pass all frequencies below a specified limit and eliminate all above that limit. This ideal filter would also have a perfectly linear phase response. But ideal filters don't exist. You need to have some compromise here with filters' amplitude and their phase response. There's 4 main types. There's a Butterworth, which has a pretty good amplitude response and then a relatively linear phase response. There's a Bessel filter, which again has a pretty good amplitude but a more linear phase response. And so those are the 2 most common filter types. Then there's the Chebyshev and the elliptical, both of which have a much steeper amplitude response, but that comes as a consequence of having some ripples, and then the linearity is, it's not linear at all actually in the phase response spectrum. So something to note here is, people have a 1 kilohertz filter like those plots I generated in MATLAB. They kind of expected they're going to get uniform passing of all sine waves up to that 1 kilohertz filter rate, and then it's going to drop off below there. But that's not quite the case. If you see for the Butterworth, you start actually filtering at 800 hertz or so, and for the Bessel, it starts kind of filtering at even as low as 200 hertz. And this is for a 5th order filter, so you'll see normally the order size, which just defines the steepness of that roll off. So generally, the higher the better. But the key takeaway here is Butterworth is for vibration testing and Bessel for shock testing. And generally, don't touch Chebyshev and elliptical unless you know what you're doing and really only interested in the amplitude. Now that you've selected your equipment, it's time to set it all up. The first thing you need to think about is the mounting of your accelerometer, and it's something that I've spoken to customers or seen their test setups, and they've completely ignored this. And it's actually a fairly critical part of your testing. There's the probe tip, which is that first blue line, that has the lowest resonance, and that's when you're actually pressing the accelerometer against the test article. If you have a pole magnet, the orange line, that's a curved magnet, you'll be a little bit higher, and then a flat magnet's even higher. And then after you get past those, adhesive mounting pad, which is like a cement type thing, or even a regular adhesive and stud mounting, they all have resonances well above 10 kilohertz. Stud mounting will basically have the max sensor response. So whatever that is, your mounting didn't influence it all. The key takeaway, though, is if you have a good adhesive which is adequately compressed and is thin enough, then you're going to have a pretty good frequency response that for most applications will be plenty good enough. You know, a lot of vibration testing, you're going to be in the kilohertz or maybe low kilohertz range, and as you see, adhesive is flat up until around 5 kilohertz. So that's something to take away. Now, I got this plot, we edited a little bit, but we got the scalable vector graphic from this website, DAQ. They actually have a pretty interesting and useful little vibration testing quiz that I'd encourage you to go check out, and you'll see that plot there. But they have some more information that we're covering relatively well in this here, but I just wanted to make a note that they have a pretty good quiz there. But let's talk about some more things about mounting here in the next slide. So I got this plot and slide off of a nice article on Meggitt and DevCo's. They have a slideshow on accelerometer mounting. Now, there's a lot in it, but we're going to cover it briefly here. Once you've decided the adhesive type, it's important to pay attention to grease and as well as torque. So those two lines of blue and yellow represent if you have a sensor, if you didn't use any grease, you have these ripples and a much lower natural frequency than if you did actually use grease, or we actually use petroleum jelly sometimes, but some type of grease. And then the blue line is if you under torque it and have no grease, you have this even more significant shift to the left and a ripple. And that's something that's really important. With our slam stick products, we give away this double-sided tape that's really good. It's very thin. It's 5 mils. But if it's not well compressed and well torqued down, if you just kind of lightly put it on, it's going to really affect your resonance and your measurement range. And if you do have the ability to torque something down, it's important to put some petroleum jelly or grease or something to make up surface imperfections, and it really will ensure that you have adequate coupling between your accelerometer and mounting surface. So again, there's a lot of information on Meggitt's website there, but I just want to stress mounting your accelerometer is very important and can give you bad results if you don't properly mount it. One of the biggest pains of vibration measurement is typically how to deal with wiring. Wiring can sometimes require modifications to the test environment and to accommodate the sensors and wires to DAQ systems. And this can limit where the testing can occur. But even if you don't have to modify the environment, you have to pay attention to certain aspects about wiring. One is that you can get these ground loops where you have this unwanted difference in the electrical potential between the sensor and the instrumentation. And this can lead to really erroneous results. Something else to pay attention to is electromagnetic noise, or EMI. Certain environments like those on surface ships will have a very high EMI environment that will add noise to your sensor. Something else to consider is mechanical noise, where the wires can induce vibration into the accelerometer itself, and that would sully the recording. And then, of course, the biggest concern is that you can lose connection. I still remember the CEO here at Mide getting all fired up at one time when we did this testing, and he lost connection during the test and didn't realize it until an hour or so later. So all that was lost. He's a big proponent of just trying to get rid of wires. So obviously you can only do that when you have a data logger, something that embeds everything together. But if you don't have the luxury to use a data logger or something, the best practice is keep those wires as short as possible. And you may have to consider certain types of wiring and more expensive wires to eliminate noise. And they have some accessories to help prevent against mechanical noise and everything. So there's a lot of information about sensor wiring, but it's something that you definitely have to pay attention to. Besides just the shock and vibration levels, you need to think about the general environment that you're going into. One key thing is piezoelectrics are temperature dependent. If you dive a little deeper into an accelerometer, it has a mass and a spring, and it uses that spring stiffness to basically define its sensitivity. And so if that spring stiffness changes, which, as you know, higher temperatures make things looser and lower temperatures stiffen things up, so that will change the accelerometer itself's stiffness, which then changes its sensitivity. So they're temperature dependent and they need compensation. You can do that compensation in hardware, which some accelerometers do, or you need to do that in software where you use a temperature sensor and then compensate the piezo output based upon that temperature sensor. So one of the things to take into account are base strains. If your accelerometer is mounted on a surface that is undergoing strain, that will really significantly impact the output of your accelerometer. So I think that's something that a lot of people forget sometimes, that a lot of accelerometers are, piezo ones especially, are ones in, where the piezo is in shear, so it really can magnify straining in the surface that it's mounted to. The other ones are relatively self-explanatory. There's certain sensors that can handle those environments, and there's certain that don't. Something else to think about are transverse vibrations. If you have a triaxial accelerometer, you'll need to know that there's going to be some crossover of x-axis vibration into y and some into z, and it's important to pay attention. The other thing is you need to know what your DAQ is going to see. Is it going to have to be in this environment? Is it wired to it? You need to make sure it can survive that. It's important you can't forget, only think about just the accelerometer. If you have a DAQ, you need to think where that's going to live and make sure it can survive as well. Now we can get into the good stuff, which, assuming you have a good setup and good sensors and DAQ and everything, you have data, and now we get to analyze that data. This is fun. When analyzing vibration data in the time domain, which would be amplitude plotted against time, you're limited to a few parameters that you can use to quantify the strength of your vibration profile. Those being the amplitude, the peak-to-peak value, and RMS. And I use just a relatively simple 60 hertz sine wave to call those out. RMS is the root mean square value. Some people question why you'd ever want that, but that's actually a really good tool to use because it takes into account the time, and thus it also, because it has time in there, there's an energy associated with RMS levels, so it can give you an indication of the destructive capability of the vibration. But generally you see the key points, and one of which is called out there, which is a period of your oscillation, and that's equal to 1 over the frequency. But normally in real world applications, you don't have a simple 60 hertz sine wave. There's a lot of frequencies, and that's why you need to go to the spectrum, which we'll talk about next. So the time domain doesn't tell the full story of vibration. Generally, there's a lot of different frequency components, and you need to use a Fourier transform to compute that frequency spectrum. Now, quick thing about FFTs, which are fast Fourier transforms. They're just a discrete Fourier transform that takes advantage of the symmetry in sine waves. And there's a myriad of FFT algorithms out there, but generally most software programs will have a fast Fourier transform for you to use, and FFTs have now become synonymous with computing frequency spectrums. The key takeaway, though, here is that FFTs depend on the number of samples. The top plot is for just a tenth of a second set of data for when I manufactured a waveform with a 1G 22 hertz signal, a 2G 60 hertz signal, and a 1.5G 100 hertz. And as you see, if you compute the FFT on it, it's really jagged. And that's because the FFT, the bin width of your frequencies, is directly proportional to the length of your FFT. And so if I compute now an FFT in those middle plots 5 times as long, you get a much more accurate spectrum representation of the data. Now, the last plots are showing you that if you add noise, the time domain becomes even more difficult to discern anything from. And if you look at that kind of noisy plot on the bottom, it's very difficult to see those 60 hertz and 100 hertz and 22 hertz signals, but the FFT clearly picks it out, and you see that broadband noise in addition to it. So let's use a real world example though next. So on the left, on that top left plot, is the time domain data from when I put a slam stick on the engine block of my car, which is a Saab. And I started the car. I actually got into the car. You see that small little spike when I got into the car. And then I started the engine. There's an initial spike, and then I let it idle for a little while. And then I just rev it a couple times, let it idle, and then turn off the engine. So you can kind of see that from the time domain. You can see that kind of strength change, but you wouldn't know the frequency of those different areas. So if I compute an FFT, which is just do a FFT of the entire signal, it looks a little noisy because it has to take into account that certain times I was doing idling, or certain times I was revving at a couple thousand RPM. And if you look at the FFT, the whole thing, it looks a little confusing. You wouldn't necessarily be able to see that much from it just you just know that there's a lot of vibration in there in the range of, tens of hertz to a couple hundred hertz. So what you use in this instance is a spectrogram. And a spectrogram basically takes a series of FFTs. So in this example, I think I took an FFT for every quarter second, and then you stitch them together and you plot the amplitude kind of shifted on looking at the plot from above, because you made now a three-dimensional plot. And that's that on the bottom left. You see that frequency, the most powerful frequency range when I first let it idle is low there, and then I rev the engine. You kind of see those waves as I rev it. So spectrograms are really a great tool to use when you have a changing vibration environment. And I go through these examples in a lot more detail on the blog. And I encourage you to check it out. But that other plot on the right is definitely a pretty picture that we love here, but it's pretty interesting data. This is from a aircraft vibration, and I think it's on the outside of the aircraft. And you can use a spectrogram this is what a spectrogram is in a three-dimensional plot. The bottom left one is if you're looking at a different set of data from above. But you see clearly in the spectrogram the frequency components and how they change with time. It's a really powerful tool. So FFTs are great when you have a finite number of frequency components, but PSDs, or power spectral densities, are used to characterize vibration environments with many different frequency components. And the reason they're a great benefit to use is they normalize the FFT to the frequency bin width. So when you're doing an FFT of a varying a varying length of a signal, your amplitude of that FFT will change potentially depending on the length of the signal. A PSD, though, takes into account the varying length of the FFT and the bin width to normalize. And you can see from this example here, I'm showing the time domain data on the left of actually the same data set that was in the slide above from the aircraft on the right, the spectrogram. And you see the middle columns are FFTs of different areas of from that vibration environment on the aircraft. And you can see the amplitude changed fairly significantly from each FFT subset of this large data set. But the PSD levels stay pretty similar the whole time. And that's a very important takeaway. The other thing with benefit with PSDs is you can actually integrate the area under the curve to get RMS vibration levels. So PSDs are typically shown in test standards, and they are used to quantify your vibration environment and use that information to design your system. We'll get into that, though, in a couple slides when we talk about the response spectrum. But now let's talk about some transmissibility. So transmissibility is the ratio of a response of your system to a given excitation input. So there's a couple plots here. They're showing similar things, but if you think of a building during an earthquake, you'll want to know how that building responds to the earthquake or to a given frequency range of input. So what you do is you calculate a transmissibility function. And what this is plotting is on the x-axis is the frequency ratio of the vibrating input to your natural frequency. So if you had the building that had a resonance of 10 hertz and the earthquake was vibrating at 1 hertz, you would have a 0.1 frequency ratio. But on the other hand, if your building had a 1 hertz vibration or natural frequency and your earthquake was vibrating at 10 hertz, you would have a 10 frequency ratio, and you would actually be damping out the vibration from the earthquake. And a couple things to note here: if you have a natural frequency that's quite a bit higher than the input frequency, you are basically the response is approximately equal to the input. And if you have, on the reverse of that, if you have a natural frequency that's quite a bit lower than the input frequency, you will be isolating or damping the input. And isolation or damping occurs once you're roughly twice, or I think it's square root of 2 for an input frequency versus your natural frequency of your damper. So damping will come into play. Q is equal to 1 over 2 times your damping coefficient. That's the quality factor, and that will dictate the amplification during resonance, but it also defines how well isolated you are once you're on the right-hand side of that plot. But there's a lot of good equations out there and ways to calculate transmissibility. But for the most part, transmissibility is just kind of a nice thing to understand. It's good for isolators and dampers. But for next slide, we'll talk about the vibration response spectrum, because a lot of times you have vibration environments with a range of frequencies. It's not just moving at one defined rate. And so then you'll need to basically do a response spectrum, which is kind of calculating transmissibility for a range of different inputs. So let's talk about that next. So in that last slide, we looked at the response to just a single frequency input. But most environments in general have a range of frequencies, as I talked about, and as I said, PSDs are used to quantify that vibration environment. So what you do as a design engineer is, if you know the design environment that you're going into, you can get the PSD and use that to go through to calculate the vibration response spectrum. And what that does is it shows you, for a given natural frequency of your environment, or your system, how it's going to respond to the excitation input. So that top left plot are responses to different natural frequencies, and the plot on the top right is basically computing the max acceleration levels for a range of given natural frequency inputs. And you'll see that the worst case scenario would be if you're at 650 hertz. So as a design engineer, and again, that's for this particular environment, but as a design engineer, you use a vibration response spectrum to either go well above the worst case or well below the worst case. And a key note here is PSDs are great and they're in a lot of test standards, but there's definitely times that you might need to get this PSD yourself. And data is king here. You need to have the data to do any analysis. So just keep that in mind. You can also take test data and calculate a PSD from that, and that you can use as design criteria for whatever design you're doing. I was able to use Tom Irvine's MATLAB GUI to generate these plots. And again, there's a link there on the bottom left. I really encourage you to check out his resources. It's incredible, the stuff he has out there, and he has these webinars that go through all this in much more detail. So please check that out. So similar to the vibration response spectrum, you can calculate a shock response spectrum. So, and again, you'd use this as design criteria for a given input. You'd want to know what natural frequencies to avoid and which ones to kind of design for. So I have a video here that I'll try to play here in a second, but it shows you a varying different natural frequencies of these springs. So the one on the far left is a 16th of a hertz. The one on the far right is 4 hertz. And then it goes up by orders of 2 in between. And you can calculate for a given 1G 1 second half sine pulse what your response is going to be. So that bottom left plot is showing the acceleration levels of your mass at different times relative to the input. And as you see, the higher frequency 4 hertz spring really tracks the input acceleration pretty well, whereas the lower frequency ones actually dampen out the vibration levels. And some of the springs that have natural frequencies around bad areas to be, like the 1 hertz, it's amplifying the input. So the input's only a 1G 1 second sine pulse, but you're actually getting over nearly 2 Gs for certain frequencies. So the middle plot, though, is important to look at, and that's the absolute value of the displacement that you get. And the reason that's important is, if you look at the plot on the left, you're like, oh geez, I want to be as low as possible. And that's true because you're dampening out the acceleration, but that 16th of a hertz spring has to withstand nearly 1,000 inches of displacement, relative displacement, to be able to fully dampen out that input. And for certain applications, that just is completely ridiculous. And obviously this is just an example. But a damper needs to make sure that you have enough displacement. And there's certain applications where you can't use a damper. you need to have very tight tolerancing between components. So you need to do stiff mounting. But you can use this shock response spectrum to figure out which resonances you should avoid and be above or below. And again, it's important to pay attention to displacement, though, if you're going to try to go the route of a damper. But let's see if I can get this video to play here. So this video is from Tom Irvine's Vibration Data Webinar 23. He goes through it in 10 minutes or so during that webinar, but we'll try to go through it quickly just twice here. You saw in the beginning that 1 second half sine pulse excitation, and now these masses are responding to that excitation. We'll have it play again in a second, but the natural frequencies from left to right is a 1/16 of a hertz, an 1/8 of a hertz, half hertz, quarter hertz, half hertz, 1 hertz, 2 hertz, and 4. So they go up by orders of 2. And we'll play again in a moment, but you can see that middle one, which is a 1 hertz natural frequency of the spring, it's still moving, even though the base input isn't contributing anything more, but it's still so significantly affected by that input that it continues to oscillate for a while. So here it is again. Here comes the input. You'll see on the far right, the thing tracks pretty smoothly with the base input. The one on the far left didn't move much at all in absolute terms, but relative to that base input, it had to withstand a significant compression of its spring. And then those middle masses were significantly impacted by that base input. And what's interesting is you'd see this 1 second 1G half sine pulse. You'd expect half a hertz to be the worst case, and it's pretty bad, but it's actually somewhere between a half a hertz and 1 hertz that's the worst case. But again, Tom Irvine covers this in more depth on his webinar, but a good quick overview here. So there are a lot of shock and vibration analysis software options available to you. The main question to ask is, do you want to write your own analysis code or use a standalone package? There's kind of pros and cons to both. If you're writing your own code, the most well-known languages would be MATLAB and Python. MATLAB, you probably have familiarity with it if you're an engineer and went to school in the United States. I'm sure it's similar elsewhere too, but engineering universities use MATLAB in their curriculum. MathWorks, that makes MATLAB, they're pretty clever with their licensing prices and everything. It's much cheaper for students than it is for commercial entities to use. And so, you typically come out of school with a knowledge of MATLAB. It was developed for linear algebraic operations and analysis, so it's very good in this particular setting. Python, on the other hand, is open source. It's free, but there's a lot of libraries out there, so some people can be a little overwhelming to have to compile all these things together. But it is free, and I actually wrote a blog comparing MATLAB and Python to vibration analysis. If you're worried about costs, Python's a great option, and if you're doing anything other than vibration analysis, Python is arguably a better option than MATLAB. So I'd check those out. If you're not necessarily that comfortable writing lines of code, but still can think through algorithms of analysis and all that, you can look into these block diagram environments, which are typically used for data streaming, but they can certainly be used for post-processing data as well. MathWorks, which makes MATLAB, has Simulink, which is based upon MATLAB. That's $3,200, and then National Instruments is probably the most well-known, and LabVIEW. I'm sure most engineering companies have a LabVIEW license or two. They also have a sound and vibration toolkit, which is $2,000. So those get fairly expensive. So MATLAB or Python might be something to consider. For standalone GUI packages, the best free one that I've come across is Tom Irvine's Vibration Data. He has a MATLAB and Python package. I use those. I use the MATLAB one to generate the plots in the last 2 slides. He's got tons of webinars that go through those packages, so you can get a feel for how they're used and how they're used effectively. And the MATLAB one, you need a MATLAB license to run it, but it gives away the code for free. And the MATLAB one, it definitely seems a little more robust, and there's a lot more options in there than there's in the Python one, but the Python's still pretty good too, and it's free. Another free software is our SlamStick Lab. It currently only works with SlamStick recorders, but it's good at giving you a quick overview of the data and can generate PSDs, FFTs, and spectrograms. But if you need to do more in-depth analysis, it exports data, and then you can do that in MATLAB, Python, or some other software. So that's available to download on our website, actually, if you want to check out with a along with some example recordings to get a feel for it. There's other software available that you can buy, which includes this M&P analyzer, this vibration view, and then Brewin Cager is an accelerometer company, but they have some analysis software packages. There's also Pro Analyst, which I came across recently, which can calculate vibration levels and motion just from a video file. It's pretty interesting. But these software packages are going to run you $5,000, $10,000, $20,000, some of them. So, but for certain applications, the cost is not a concern, and those give you a lot of really good options to analyze your data. So I know we went through quite a lot in a quick 45 minutes here, but I'll just try to conclude quickly and then give you some links for resources and then take questions here in the last 10 minutes. To summarize, again, shock and vibration measurement is an art and a science. It's not like you follow these 3 steps and you get great results. There's a lot of different give and take that goes into it, and not every application is the same. So there isn't just one rule of thumb to use across all things. So I really like that definition. I think it really hits shock and vibration very well. Again, you need to, going back to one of the first slides, you need to answer a couple questions before you can dive into the accelerometers that you want to look at and different DAQ systems, and even before you can set up what analysis you're going to do. You need to understand what you're testing, why you're doing it, who the customer is, when the testing needs to occur, when the analysis needs to be completed by, and where, of course, all this testing is occurring. Analysis is the best part, but it's also the most critical and sometimes the most difficult part. So please explore, the software options available to you, and refer to that slide previously on that. But there's tons of options, so definitely look into those. And if you're comfortable running your own code and comfortable with the math, I encourage you to do that, because it really helps you better understand what's going on behind the scenes. In summary too, though, there's tons of resources, so please utilize those. And next slide here, I'll just go show you some options. We have an ebook that you can download for free on our website with that link that goes through everything that we discussed in the webinar now with much more depth, and has links to everything as well. But there's 2 links here I want to call in, which is Tom Irvine's vibration data blog, and then of course our Mide blog has a lot of great resources. Megid and Devco, which is an accelerometer company, as well as PZB Piezotronics, they have great technical papers, and I would check those out. And then there's some books you can buy. We have them here. You can get them on Amazon, and they're great resources too if you want to dive in deeper. But there's tons of resources out there. I really tried with this ebook to compile those resources in a clean way, because I know there's just, as I did the research myself, there's just tons of stuff out there, and it's hard to kind of go through it all on your own. So hopefully you'll find that ebook as a nice tool to give you kind of a jumping off point to dive into different areas deeper if you find the need to do that. So, but now I think let's try to take some questions.
Stephen, thank you very much for that great presentation. We do have some questions that have come in from our attendees, and we'd like to let them know if we don't get to their question, don't worry, we'll have an answer for you following the webinar. The complete Q&A transcript, including answers we don't have time for, will be sent to all of our registered attendees and will be posted with the webinar when it goes into the on-demand mode. Okay, now let's move on to our first question, Stephen. How do I go about qualifying my product to meet the MIL standard 810 shock standard?
Thanks, Rich, and to whoever asked that question, that's a good one. Those MIL standards are really in depth. I remember for one of our development programs, I spent weeks trying to go through 810. There's a ton of information there. One of the things people don't understand on the MIL standards is a lot of times those standards are just kind of they're rules of guidelines for testing, but they always kind of suggest you should go get real data. And so that's kind of one thing I'd say. If you're doing MIL standard 810 testing or some other testing, you're going to need to rely a little bit on the Navy or whomever you're doing the testing for to provide some data for you. And if they say they don't have any available, that might be a good time to offer to get that for them, because that could be really useful for your program and maybe even for the Navy and other programs that they may have. But assuming you have the data, you'd have to go through all the things we talked about in this presentation today, which make go through good practices on getting the data and then analyze it with some software programs you might have available, or writing your own code in MATLAB or Python. The big thing with mill standard testing is you communicate as much as possible with the Navy, and they'll have people there to help guide you along a little bit as well. But the most important thing is just trying to get accurate data to test your product too. But it's hard to do sometimes.
Okay, Stephen, thank you for that answer. Here's another question. We are new to shock and vibration testing, and we aren't comfortable doing our own testing. Do you know any consultants you could recommend?
Thanks, Rich. Yeah, I mean, I can understand that shock and vibration testing as a whole. There's a lot to it. We tried to cover a good amount of data, a good amount of information in this quick hour, and we ran through a lot of it. So it can definitely be very daunting to have to do this testing analysis yourself. I would say, there are products out there on both the data acquisition side and the analysis side that should make it a little easier. Some data loggers that have everything in one might make your life a little easier with not having to get a bunch of different components and wire it all together. But and same on the analysis side, there's programs that are pretty well put together. Tom Irvine's GUI packages that he has webinars that go through it, and that might be a good thing to look into. But if that's still something that you don't feel comfortable doing yourself, the only consultant that I've personally worked with would be Tom Irvine, who has something like 40 years experience in this field. His website, which I mentioned a couple times, at Vibration Data, WordPress.com, or one of the other, that's a great resource, and he does offer consulting services. So I'd start there to learn for yourself, but also maybe end there if you decide to go the route of a consultant. He'd be a great option. So that's a good question.
Again, thank you for that answer, Stephen. Here's another question. We need to demonstrate to our customers the effectiveness of our shock and vibration dampers. Do you have any recommendations for tools to help get the data, and recommendations on how to present the data?
Thank you, Rich. And again, to whoever asked that question, that's another good one. This is definitely a great application for using shock and vibration test equipment, would be to qualify the effectiveness of your damper or isolator. I haven't personally worked on doing that, but there's some customers of ours, Slamstick, that have done this. And what you'd want to do is qualify or quantify the vibration environment without your damper, and you'd use some accelerometer or some DAQ system to do that. Generate a PSD of that environment without the damper, and then put your damper on the in that environment, and then the accelerometers on your damper to then get another PSD or something to quantify that vibration environment. And then you could potentially use a vibration or shock response spectrum to show how much you are isolating and attenuating that signal or that input. The thing that I haven't really touched on, I guess, in this webinar, and is something to talk about a little more in depth in that ebook, which would be simulating some shock and vibrations in the lab with a shaker system. So that might be something you'd have to do if you're developing a isolator or damper. Would be to get a shaker system. They can run $30,000 or more, so you might have to go to an outside testing facility like NTS to do the testing for you once you've developed that product. But I would use a PSD and the shock and vibration response spectrums before and after, or with or without using your isolator, as a way to present the effectiveness of your product. And again, that GUI package of Tom Irvine's, but there's other ones as well that show those shock response spectrums. You can really hammer to your customers or whomever the effectiveness by showing reduced accelerations that their components would see through a response spectrum. So that would be the way to go there.
And Stephen, thank you once again for that answer. Here's another question. Can you tell me a little more about the product you developed?
Thanks, Rich. Yeah, I mean, that's feels like kind of a softball question there. So, and I know you guys are short on time. We're short on time as it is, but That wasn't really the point of this webinar. Was really just to educate people on shock and vibration testing and all that goes into it, not necessarily to promote the SlamStick product. But there's certainly a lot of information on our website. It's a shock and vibration data logger that kind of was designed for ease of use. So maybe that's all I'll say there. But if you just search for SlamStick, it's easy enough to find, and we have a lot of good content on our website there. But again, it looks like we're running short on time. We covered a lot today. I really appreciate everyone's participation, and any questions you had asked that I didn't get to right now, I'll be able to personally respond to, and I think they might be posted for other people to see as well. So I'll definitely get to all the questions you may have. I'm really excited that there are so many questions and people are so interested, because this is an important topic for a lot of design engineers and everyone else as well. So again, I really appreciate the time, everyone, and hope to talk to you at some point or other about shock vibration testing. Thanks, guys.
Stephen Hanley, thank you for spending some time with all of us today. Thank you for taking the time to join us today. Take care, and we'll talk to you soon.